Very good afternoon, everyone. This is Dr. Shaik Shafi, working as Associate Professor, the Department of ECE, BV Raj Institute of Technology. Today, we are going to learn about the concept random variables, which is related to the probability theory stochastic process subject. Now, we will move on to the introduction to random variables. See, in the earlier sections, we have seen introduction to probability and the basic problems related to probability theory, and later we moved on to classification of probability, that is joint probability, conditional probability, total probability, and extension to total probability Bayes theorem. So we have covered all these things. Now we will move on to random variables. Random variables. First of all, before entering into random variables, why we need to go for random variables and what is the importance of random variable? See, we have come across some of the random experiments like tossing a coin. Tossing a coin. So, what are the outcomes? We are familiar with the outcomes, that is sample space, head, tail. So, the outcomes of this experiment are descriptive in nature, that is head and tail, which are not numericals. To know the behavior of the random experiments whose outcomes are descriptive in nature, we use random variable. Random variables. So, random variable is a function, is a kind of function which assigns value, numerical values to the outcomes of random experiment where the outcomes are descriptive in nature. So, suppose example what we have taken, S sample space, the outcomes are head, tail. Now, we will assign using random variable the numerical values to the outcomes of the random experiment in which the outcomes are descriptive in nature. And random variables are denoted by capital X, and the elements in the random variable are denoted by small letter x1, x2 and so on. Now, we will see how random variable is assigning values to the outcomes of descriptive experiment. Suppose now we will take a random variable x denotes number of heads in the experiment. Now random variable x, which denotes heads, number of heads, is equal to, now number of heads in the first sample is 1 and the number of heads in the second sample is 0. Now rearrange this one as 0 comma 1. Now random variable is 0 comma 1, where 0 indicates number of heads 0 and 1 indicates the number of head only for one time. Similarly, you can extend this for another example, that is tossing a coin for 2 times. The sample space is S is equal to head head, head tail, tail head, tail tail. Now again we will consider x random variable for which denotes number of heads. So in this case the number of heads are 2, in this case the number of heads are 1, in this case the number of heads are again 1, in this case the number of heads are 0. Now rearrange the terms like 0, 1. If you have twice 1 and 1, you mark it as only for one time. The reason for marking this I will explain in the conditions for a function to be random variable. So this is the random variable for the experiment where tossing a coin for 2 times. So because of this numerical values, now we can able to give the behavior of the random experiment in which the outcomes are descriptive. So for if you have numerical ones, now easy to plot the graph. Then from that graph we can extract the behavior of the random variable. Now we will see what are the conditions for a function to be random variable. So all the functions need not be random variables. So there are some constraints for a function to be a random variable. First one, every sample in the sample space must have only one value on real axis. What I mean to say is, suppose we have seen sample space in a tossing a coin for one time, the outcome is head tail. Now each and every sample should have only one value on the real axis, that is number of times head is appearing is, here it is 1, and the number of heads appearing in this case it is 0. So the values, each and every sample in a sample space should have only one value on the real axis. Head should not be pointed to 1 as well as 0. So one sample should have only one value. Then that is first condition for a function to be random variable. Second one, for a set x less than or equal to x, probability of x less than or equal to x is defined as sum of the probabilities of individual random variables. So suppose probability of the set x less than or equal to x1 is defined as probability of x equal to x1. This is valid if you have random variable set as x as x1, x2, x3, and you have got corresponding probabilities here and here for the particular random variable. Now suppose if probability of x less than or equal to x3 you want to define, then it will be written as probability of x equal to x1 plus probability x equal to x2 plus probability x equal to x3. Here when you are finding the probability of the last random variable, the sum of the random variables probability will be equal to 1. This is default and it will be explained with the help of an example. So here the point is, the probability of set of random variables x less than or equal to x must be is equal to sum of all the probabilities of the individual random variables. This is also one more condition. The third condition is probability of the set x equal to infinity and probability x equal to minus infinity. The values must be equal to 0. So when x is equal to infinity, then the probability of x is equal to infinity is equal to 0 and probability x less than or equal to infinity equal to 0. So these are the three conditions to be satisfied for a function to be random variable. So what we have seen is random variable, introduction to random variable. So with this I can conclude the definition of random variable as random variable is a function which assigns real value to each and every outcome of any random experiment which are descriptive in nature like head, tail, these kind of thing, where we cannot find the characteristics without numerical values. So we are converting that descriptive into numerical one on a real axis. So function value to which the each and every outcome of a random experiment which are descriptive in nature, so assigns on real axis, real axis. So this is the definition of the random variable. Now we have got classification of random variable, different types of random variable classification. Based on the nature of the random variable, the random variables are categorized into three different types. One is continuous random variables. The second one is discrete random variables. Third one is the combination of both, that is mixed random variables. RV indicates random variables. Now definition of the continuous random variable. So a random variable is said to be continuous if random variable consists of n number of random variables, that is x equal to 3.5 less than or equal to x less than or equal to 5.5. So it is a range. The range of values are from 3.5 to 5.5. So if you consider there are number of values from 3.5 to 5.5, that is 3.5.1, 3.5.2 dash dash, then up to 5.1, 5.1.1 to 5.21. You can take n number of values up to 5.5. So here the number of values are more in number. We call it as a infinite number of values almost. So that kind of random variable is what we call continuous random variable. Then second one is discrete random variable. So it is defined as a random variable is said to be discrete random variable in which the number of random variables are elements are countable in nature. We can count a finite number of values, 1, 2, 3, 4, 5. Here you can count the number of samples here, 1, 2, 3, 4, 5. So these kind of random variables are called discrete random variables. And another one is the third one is mixed random variables. It is defined as a random variable is said to be mixed random variable, which is a combination of both the continuous as well as discrete. That is x equal to, suppose 1, 2, 3 and 4. From 4 we have got a range, set of values are there. Here infinite number of values are available from here to here, and these are finite number of values. So this random variable is mixture of combination of both continuous and discrete random variables. Now after classification, if you see, we have got probability distribution function. We have got probability distribution function. So this is shortly known as capital PDF. Then the question rises here is why we are going for probability distribution function. So as we have got random variable, different classifications we have seen. For discrete random variable, in case of the second case, the discrete random variable, to know the behavior of the discrete random variable, we are going for probability distribution function. So it gives how the discrete random variable is distributed on a real axis, that is can be visualized using probability distribution function. So for example, this can be and it is denoted by capital Fx of x, and whose formula is probability of x less than or equal to x. So this is the mathematical notation for a probability distribution function. This we have seen in case of conditions for a function to be random variable. The second condition where the set x less than or equal to x and whose probability gives sum of all the probabilities. So here we will see one example how the distribution of a random variable can be explained and can be plotted with the help of the probabilities, individual probabilities of the random variable. Suppose if you take a question like this, in an experiment, any experiment, that could be any random experiment in which the random variable x has elements such as 1 comma 2 comma 3 comma 4 comma 5 comma 6, and each and every sample has got element, has got the probabilities, corresponding probabilities with px of x, where capital X is the random variable and small x is the element of the random variable, that is 1 2 3 4 5 6, and each and every random element has got the probabilities like 2 by 36 and 8 by 36, 12 by 36, 7 by 36, 5 by 36, 2 by 36. So, these are the corresponding probabilities of the element, individual element. So, here it is this one and this one, and here this one, and this is this one, the probabilities. Now, we need to find plot distribution function fx of x. Plot in the sense we need to draw the characteristics of the distribution function with respect to the random variable. Now, plot means the graph between fx of x and the elements of the random variable x. Now, how to plot this one, that we will see now. Now, first we will find as per the formula, fx of x says probability x less than or equal to x. Now, this 1 and 2, all these are called elements of the random variable, which are denoted to be x1, x2, x3 up to x6. Now, first we will find the distribution of the random variable first element fx of 1. This you can write it as fx of x1 also. Now, fx of x1 or fx of 1, which is mathematically x less than or equal to x1, or probability x less than or equal to 1, where x1 is equal to 1. Now, with this, which is equal to, can be written as x probability x is equal to 1. So, before 1 there is no any other element, so we are considering up to equal to 1. Then according to that, the probability, corresponding probability is what? 2 by 36. 2 by 36. Now distribution function for another element, second element, is fx of 2, which is equal to probability x less than or equal to x2. Now, as I said in the second case, as I was mentioning here, the set probability x less than or equal to x3, if you take, that is sum of the probabilities. This is one of the condition for a function to be random variable. So, same thing we will apply here. Here probability x less than or equal to x2 is, so it can be written as probability x equal to x1 plus probability x equal to x2. Now, the value of this one is what? 2 by 36, and value of this one, probability at x equal to 2, is 8 by 36. Now, the total value is 10 by 36. This is about distribution function at a second element, that is in capital X equal to x2, then where x2 is equal to 2. Now, we will move on to next fx of x3. So, similarly, you have to follow the same thing. Fx of x3 is equal to probability of x less than or equal to x3. So, here x3 is equal to 3, and probability x less than or equal to up to 3 is, can be written as probability x equal to 1 plus probability x equal to 2 plus probability x equal to 3. So, if you add all the terms, and you will get individual probabilities 2 by 36 plus 8 by 36 plus 12 by 36. So here you will get 22 by 36. So similarly, if you take the final value fx of x6, which is equal to probability of x less than or equal to x6, which is equal to probability x less than or equal to up to 6. If you add all the probabilities, that is right from probability of x1 to up to x6, it will be 36 by 36 and the value is 1. So this can be written as fx of x6 is equal to 1 at where x6 is equal to 6. So based on these values, now we will plot a distribution function of the random variable x with respect to the elements of the random variable. Now we will take x and y axis, where y axis gives the distribution of x and it is a function of x. Now we will take on x axis the elements of the random variable x. Now as the random variables are there in the experiment, given experiment, starting from 1, 2, 3, 4, 5, 6. These elements, these are the elements of the random variable x. You mark these on x axis, that is 1, 2, 3, 4, 5 and 6. Now we have got distribution function values fx of x for the corresponding random variables, not probabilities. Now distribution functions, what we got, one is 2 by 36, another 10 by 36, 22 by 36, 29 by 36, 34 by 36 and the final one 36 by 36, which you can write it as 1 also. Now you mark all the distribution values of the individual random variable elements on y axis, right from 2 by 36 to up to the final value 1. So almost how many values you have got? 6. 2, 3, 4, 5, 6. Now for the first element of the random variable 1 and the probability x less than or equal to 1, there is no value before 1. So you can start random distribution function from 1. So at random variable at equal to 1, we have got the value is distribution value is 2 by 36. Mark up to 2 by 36 and then for random variable the element 2 is 10 by 36, then you can mark 2 value up to this point, that is 2 by 36. At 2 the value is 2 by 36. Now at 3 the value is this one. What is that? 22 by 36. So like this you continue up to, for 6 it is equal to 1 and it will be continued. It will be constant. So if you look at the curve between distribution function and the elements of the random variable, it is in the form of staircase. Each step size gives the probability. Each staircase gives the probability of the element. So if you take here the value of this one is what? 10 by 36. 10 by 36 minus 2 by 36 is what we call is 8 by 36, which is the probability of the random variable element at 2 x is equal to 2, 8 by 36. So individual staircase gives, size of the step gives the probability of the particular element. So like this you can plot the curve between distribution function and random variable. This is what we call the characteristics. This is what we call behavior of the random variable. So here the random variable type is discrete in nature, where we have got finite number of values. Like this we can find the behavior of the random variable using distribution function. So for this extension to this question, sometimes in examination somebody will ask what is the expression for fx of x. So mathematically the expression of fx of x is written as summation I equal to 1 to infinity probability of xi and u of x minus xi, where probability of xi is the probability of the individual element of the random variable and u indicates the step function. Why? Because here the graph is in the form of staircase. Usually the staircase function is represented by step function and which has got right side shift in the right side. So we are going for u of x minus xi. So this is the mathematical notation expression how to express behavior in the form of mathematical notation. So similar, we will write the expression for the same question, that is fx of x is equal to, it starts from I equal to 1 to up to 6, then probability of xi and u of x minus xi. Now remove the summation and write down probability of, in place of I, first we will write x1 and u of x minus x1 plus probability of x2 u of x minus x2, so and so forth, probability of x6 u of x minus x6. Now replace x1 with 1, x2 with 2, x3 with 3. Now in the next step write down probability of 1. Probability of first element what we have got is already mentioned, that is probability of 1 is equal to 2 by 36. Now replace the values 2 by 36 into u of x minus 1 plus the second element probability which is already mentioned, that is 8 by 36 into u of x minus 2 and so on and so forth. The last one probability of sixth element is 2 by 36 into u of x minus 6. This is the expression for the distribution function. So with the help of the random variable elements in a random variable and probabilities, we can have the distribution of the random variable curve behavior and we can represent the same thing in the form of mathematical expression, that is using step function. So this is about probability distribution function which is used to obtain the behavior of the random variable, where the random variable type is discrete in nature. Now based on this one we have got properties of distribution function. Based on the formula fx of x, we can obtain few properties, where those properties are helpful in obtaining in solving the problems in easy way. In simple manner we can have the solution. So those we will see now. The properties, first property says fx distribution of the function infinity, which can be written as per the above formula, probability of x less than or equal to infinity. So up to infinity we have got number of elements, then summation of all the elements, that will lead to probability of sum of all the elements will be equal to 1. Now as we have seen here, the number of elements, the final element is 6, the distribution of up to the final element is equal to 1, what we have got here, this one, this one, this one. So like that, similarly that will be extended for the infinity also. X less than or equal to infinity is equal to 1. This is first property. Second property is fx of minus infinity, which can be written as probability of x less than or equal to minus infinity. Now as there is no element before minus infinity, it is not possible to find the distribution function. This we can write it as is equal to 0. So overall the distribution function lies between, the third probability small x lies between 0 and 1. The final maximum value is 1 and the least value is 0. Now fourth property fx of x1, the first element, is all the time less than that of less equal to the second element distribution fx of x2, where x1 is less than x2 or x2 is greater than x1. So next The fifth property is probability. If you want to find the probability between two elements of the random variable, we can have x1 less than capital X less than or equal to x2. The formula for this one is fx of x2 minus fx of x1. So here it indicates that when you go for the distribution, the higher element minus the lower element, fx of x2 minus fx of x1, it is all the time, if even if you want to find the probability between the two different elements, x2 less than x less than or equal to x3, here also the distribution is the difference of these two, that is fx of x3 minus fx of x1, where x2 is greater than x1, the element. Then the last property is distribution function of a real valued positive value is always positive distribution. Fx of x plus gives the positive value, which leads to the distribution of the positive random variable, the element of the random variable fx of x. These are the properties of probability distribution function. 6 properties are defined, which are useful for identifying the behavior of the random variable at any instant of time. The any instant of time in the sense at any point of element of the random variables. Now, as a part of exercise, you try at home that find fx of x expression. What I mean to say is expression and plot in the sense give the behavior of the distribution function fx of x for the experiment. What is that experiment? Tossing 3 fair coins at a time. 3 fair coins in which consider the random variable, chances of getting tail. So here you need to define a random variable for in a random experiment in which 3 times a coin is flipped. Write down the sample space before getting into the random variable. First write down the sample space. That is head, tail, head, and so on and so forth. Total how many number of sample space? Finally it ends with t. So 2 power 3, total 8. 2 indicates number of outcomes in a tossing a coin, head and tail. How many number of times you are performing that is 3. So total number of sample space in a short way, as we have discussed earlier, is number of 8. Now later then define a random variable where x denotes the number of tails in the experiment. So number of tails maximum it will be 0, 1, 2, 3 times you will get. So random variable is 0, 1, 2, 3. Now for this corresponding probabilities you have to define. Based on the sample space. Then go for finding the distribution function table. Then go for finding the distribution function expression using the formula I equal to 1 to n probability of xi and u of x minus xi. Then plot the characteristic curve between distribution function and the random variable elements x. So you try this at home. We will see a few more problems in the next session. So this is for today. So hope you have got the concept of random variables under probability theory and stochastic process. In that we have seen random variable is the one which is used to find the behavior of the outcomes of the random experiments in which which are descriptive in nature. So furthermore, to find the behavior of the random variable, we have got a probability distribution function where it gives the behavior of the random variable. So to overall, in order to find the behavior of any random experiment, we have gone for probability. Then to extend to find the behavior of the random experiments in which the outcomes are descriptive, we are going for random variable. Then moreover, then if we have a discrete random variable, to find the behavior of the discrete random variable, we have got probability distribution function. So in the next class, we will see some more examples related to probability distribution function, and we will move on to how to find the characteristic of curve or behavior of continuous random variable, which can be obtained using probability density function. Those things we will discuss in the next class. This is for today. Thank you very much for attending the class.
Like, share, and subscribe. Hit the bell icon for more updates.